selected signal is very weak. We're talking usually microvolts, which is millionths of a volt. So first of all, this weak signal needs to be amplified. We'll have to amplify up to a point where we can work with it. And also our receiver, the information that's on our radio wave carrier, most commonly is audio, must be recovered. We'd have to have a means of getting that signal back. Then likewise, that recovered signal to pick out just our signal that we're looking for and get rid of the other ones that are caught there. A term called cross-modulation occurs when the incoming signals overload the receiver's front end, or it's maybe sometimes also called receiver overload. You'll actually find that if a couple of us were leaving here tonight and one of us was to transmit on our radio in their car, anybody fairly close actually find their receiver almost swamped or muted because the signal's so strong. Image frequencies, we'll talk about a little bit more detail. They're strong signals at a particular but a different frequency than the frequency we're tuned to. And very, very, very important, stability drift. We want our receiver to be very stable on the frequency that we are trying to receive, because otherwise if our receiver starts drifting, then so will our audio. Nowadays they're using very high stability synthesizers. Back in the day first signals were just straight tuned circuits, which not very stable. Then we come up with the crystal. Crystal is very stable, but problem is you need one for every frequency that you want to operate on. And noise. I borrowed a couple of slides. Always undesired. Well, we have two kinds of noise that we talk about. Natural noise, which is from the sky, thermal noise, and just inherent noise in our circuitry itself. Like our components in the radio, our circuits are going to generate a little wee bit of noise. The better the quality of components and circuits, the lower the noise level. And for your study, that's known as QRN, as natural noise, and the other one, man-made noise, QRM, noise made by sparking electrical contacts, such as machines, etc. Well, believe it or not, electrical arcs or sparks create a lot of frequency, especially even in the RF bands, just a wide band. Like lightning, for example, if you're ever listening especially on your HF radio, and there's a lightning storm somewhere around, you hear what they call static crashes. Just zzz, zzz. It's caused by the static. And they use that principle. The very, very first transmitters actually used a spark gap. They used a spark gap, and by turning the signal on and off by the length of the duration of the spark, either short or long, we had dits, das, and that's how they used to read. Very, very first Morse code was sent by spark gaps. And just doing a little bit of reading, I guess the very first, I guess we'll call them oscillators, were actually great big alternators. Like it's a term that's basically an AC generator, but because it's AC, we call it an alternator. Big, large machines, and they generated signals in the, say, around 21 kilohertz, not very high frequency, but those were the very first. Then they perfected vacuum tube circuitry. Now we could create oscillators at just about any frequency we needed. But if we were to look at on a spectrum analyzer, this is what they call the noise floor. This is the inherent noise that's there. As soon as we turn on our receiver, there's a certain amount of a noise level. It's like when you turn your radio on, no signal, you hear that staticky noise, and typically adjust your squelch control to get rid of it. When we talk about signal to noise, as I mentioned before, again, we're talking about comparing the level of our actual desired signal to that value of noise signal. And we do it in a ratio. Everybody loves mathematics, but we do it as in a decibel form, or 10 times the log of the signal power over the noise power. Or typically, let's mention the signal plus noise to noise. Noise limiters. It says, yeah, you can use a noise limiter, but can only receive noise when it's a short duration. If it's a long duration noise, it can't differentiate it. Okay, let's go one more step here. All right. Like I said here, the limitation of the receiver, any gain in the amplifier of the receiver, well, it'll amplify our signal, but also amplifies the noise because the amplifier can't tell the difference from them. So typically we'll put a noise limiter in, which will basically clamp the level to a certain maximum value. So here we're basically cutting off these noise peaks, these impulse noise peaks. We're just basically cutting them off. And sensitivity of receiver is definitely dependent on the capability of the receiver not to generate much noise internally. Okay. And some of the noise picked up from the antenna, we can diminish that or reduce that by the help of bandpass filters. And we're going back to, if you remember, capacitors, inductors, tuned circuits, which basically we use tuned circuits a lot as filters. Because remember, a series tuned circuit will provide the minimum impedance at resonance, whereas a parallel tuned circuit will give you the maximum impedance at resonance. Typical filters you'll see is sometimes 250 or 300 hertz signal for a CW signal, and 2500, sometimes more commonly is 2700 hertz bandwidth filters for sideband.
So Dave, what's doing the noise limiting? Is it a diode that's cutting the peaks off? What's cutting the peaks off?
It's more.
Or is it a filter?
It's probably it's more likely a transistor, or it could be like a Zener diode that just fires at a given point and clamps it to a given level. Quite likely could be just like you say a Zener diode with the simplest form of it.
But could you clip the incoming signal to the point it distorts it?
Oh yeah.
Yeah.
Like for example, your waveform right there, you could actually clip it lower, right?
Yeah.
So you could.
Well, if you clip it lower, you're going to start chopping off some of your
Data,
peaks.
yeah, okay.
And that's the last thing you want, really. We talk about. Okay. All right, so for our receiver, we need some sort of an accurate readout of basically what frequency we're on. You know, I guess much older radios than now, we just used some sort of an analog scale or a readout thing. Nowadays, pretty well the standard for many, many years now has just been a digital readout. Because it is very important, and by regulations you have to know what frequency you're operating on with a fair degree of accuracy. Not necessarily on the test, but maybe a little bit of history. One of the very first radios that people use, talk with crystal radio, actually what I remember, or some people not using a true crystal, it was just some form of, in this case, basically just a variable inductor, a diode, instead of high impedance headphones. No power at all applied to it, just enough, picks up enough signal from the air to just try and provide a weak signal into your pair of headphones. You know, very very poor radio, not very selective. I mean, if you have a bunch of stations that are fairly powerful, it's pretty hard to select between them. So that was kind of the first step. Then we came along what they called the tuned radio, or the TRF. Basically, so here in that particular unit, you had all these tuning stages. So basically, 3, 4, 5, depending on the quality of the radio. So you basically had all these dials, so you had to tune each one of them, get them all set right on your incoming frequency, and then we detected it through an audio signal. This is one of the first powered receivers. But very complicated, a lot of screwing around because you had to adjust all these tune stages.
Would the tuning work like a multiplier type system where you'd tune one and that would get you close?
Yeah, exactly.
Tune
Well,
the next
you
one
just
and
kind of
that would
like
do a little bit
narrow
more
down
work.
your, you just be kind of tuning closer and closer. One would be like a coarse and a finer and a finer. You'd be just kind of like squeezing it down,
Gotcha.
the signal that you were looking for. But we progressed. And the problem with something like that is this section had to be broadband enough so that we could receive all of the frequencies that we would ever want to listen to. So to make a receiver that broadband, it's not very selective, right? It's harder to tune as a specific single frequency that you want to tune.
So it didn't have a band switch. So
Not that I remember. I'm just going by pictures. I remember seeing them, but if you remember the theory is,
yeah.
but still, it just wasn't selective. Plus, you had to get all the stages tuned just right. All right, here's just some terminology. I think we talked briefly about this yesterday. The term heterodyning is where we mix two or more signals in a nonlinear device, as a tube, transistor, diode mixer. As I think I mentioned this briefly with transmitters. So when we put in two frequencies, we basically end up with a result of 4. The original frequencies, so basically like your high frequency and your modulating frequency or whatever, and also you get the sum of the two, you get the difference of the two. So local oscillator. But in the receiver we use that just a little wee bit differently. And again, this is basically kind of the same thing we're saying. A mixer is a nonlinear device, because if it was a true linear device, all it would do is just amplify and pass through exactly on the output exactly what was on the input. So in our case, we need something that's going to generate those sum and difference frequencies. That's also we say it's a nonlinear, Again, it's rehashing the same thing, sum of the frequencies, difference of the frequencies, and both the original frequencies. And we can use that for a few things. One of the applications of a mixer is product detector. We're going to get to that in a little bit. All right, using that heterodyne principle, we created what they call the super heterodyne receiver for AEM. So we start off here from our antenna. We bring in our signal to the RF amplifier. We need to amplify it enough that we can work with it. We have a local oscillator. We talked about those before. We mix them and we filter them up and clean them up. Now we've come up with something new called the IF amplifier, intermediate frequency. So what we can do in a radio, so basically we'll build a section called the intermediate frequency section. So it's always going to be the exact same frequency. Typically the one you'll see most common in back from AM radios, still used to be 455 kilohertz. So if we can convert any signal we want to receive down to that one band, we can put some really, really good filters in that one section, because all we have to do is build filters for that one frequency band, one bandwidth, in our case, say 455 kilohertz. So we can use what they call crystal filters, mechanical filters, very sharp, very good filters, because all we ever have to do is filter at that one frequency. Because by having a variable local oscillator, we can mix it with a signal, and we can receive any frequency we want just by simply mixing a local oscillator with our received signal, converting it down to the IF frequency. So that IF frequency is always the same. We convert any signal we want to use down to the IF frequency. So now we only ever have to worry about processing that one frequency band. So now we can be very selective. And once we process it through the intermediate frequency amplifier, slow down, we'd have to demodulate it. That's the reverse of modulating, like we learned the other night, is we modulated a signal. Now the reverse is demodulating it. And as we mentioned before, everybody's probably used to it, whether they know or not, used to on their computers, used to use modems. Stands short form for modulator demodulator. Now we're back down to an audio frequency. We need to amplify it enough that we can drive our speakers so we can listen to it. And some places you may call, you say another name for the local oscillator, some places they may call the high frequency oscillator. And these words are interchangeable. Demodulator or detector are interchangeable in a AM radio. All right. Two other terms you'll see referred to in radios. When they talk about high side injection, means the local oscillator frequency is higher than our received frequency. So in other words, it's going to be, in our case, if we're using a 455 kilohertz IF, a high side injection, the local oscillator frequency will be 455 kilocycles higher than our received frequency. Or likewise, if we decided to use low side injection, which for whatever reasons, I don't know the engineering why they do sometimes, but it's the reverse. The local oscillator frequency would be 455 kilohertz less than our received frequency. How are we doing so far? Questions? Is it clear so far? Don't be afraid to ask. I'm going kind of quickly here, but
So why is it called super?
I really don't know. I don't remember.
Super hat. Just not hatch. And they just call it a hat.
Yeah, there was. I'm reading somewhere. There was another one. I think it was called the Autodyne receiver, and I don't know much about that. But then for some reason they called it the super heterodyne receiver.
Yeah, I made one of those regenerative receivers.
Okay. Yeah.
Yeah, which was basically an oscillator.
See, we're talking on a very simple concept, but some radios, they actually have 2 or 3 IF stages. They actually do this, like in my Kenwoods, it actually does it 3 times. So it converts it to one IF frequency, then it converts it to another IF frequency, and actually converts it to a third IF frequency before it processes it. Okay, we talked about image frequencies. Okay, so in this case, here's our desired station. This is the frequency we want to listen to. So in this case, we're running our local oscillator at 455 kilohertz. So therefore, then our local oscillator frequency is going to be 455 kilohertz below our desired station. So when we mix them or subtract them, it will give us the difference. But we call it image frequency. So if we actually had a frequency coming in that was 455 kilohertz above our local oscillator, what happens when we mix those two together? the difference then is going to be 455 kilohertz. So we've actually got this frequency, which is quite far away from where we actually want to be, but it is being detected just the same. So we have to deal with that. Okay. And these are just some examples of what I mentioned. So for a low side injection, you're saying, okay, our desired frequency was 28 megahertz, our local oscillator being 19 megahertz. That's going to give us a IF of 9 megahertz. And a possible image being 10 megahertz. So if we mix 10 megahertz with our 19 megahertz local oscillator, we still come up with a 9 megahertz different signal. So that's interference. We don't want that. And likewise, apply the same example if it was a high side injection. Just an example of the numbers. All right, we like talking block diagrams, Dave. So now if we're receiving an FM signal, it's almost the same. We still have RF amplifier. We have our local oscillator, mixer. We filter it. Again, we run it through intermediate frequency stages. But in this stage, now for FM, remember, we don't care about the amplitude of FM signal, because any variations on it are generally just noise. All we care about is the frequency shift. So by running it through a limiter, we actually take this signal, you see the noise peaks on it, we just cut them off because we don't care about them. All we're worried about is that frequency going back and forth. Excuse me a second, tie my shoe before I fall. Basically the same, just so we're on the same page. This is the exact one out of your books. Again, antenna, RF amplifier. In this case, they call it high frequency oscillator, mixer, filter it, intermediate frequency. Product detector, and BFO. Okay. Checks.
I didn't think FM had a BFO.
What's that? I'm just thinking.
Yeah.
That doesn't look right.
Page 1311.
It's a transmitter.
Yeah, that's not. Let's somehow this one got slipped in. It's not right.
Yeah, slip over to the next later in the chapter.
We'll back to that in a minute. Okay. When we talk about CW or single sideband, we use basically the same receiver format. So again, not much difference from before. Antenna, we RF amplifier stage. We have our high frequency oscillator or local oscillator, whatever you want to call it. We mix them, filter them. That's what it is. I must put it wrong.
Yeah, that one needs a BFO.
That's what happened. The
It
two
looks like
slides, two slides got interchanged. My apologies. Okay, we'll have to fix that. This is our FM. That's why it wasn't looking right to me. All right. Again, back to here. We filtered it. We run it through the intermediate frequency amp. We limit it. Basically, we've cut off the noise. Now we have what they call a frequency discriminator, which detects our changing frequencies. And once we've basically recovered our audio, we feed it to an audio amplifier and out to our speaker or headphones. Okay, now let's go. All right, my apologies here. This is our single sideband or CW.
And CW, both.
Because remember, I will fix the titles before I send it out. Okay, remember our CW signal. What do? It's just a carrier that we turn on and off. So we receive that. There's nothing we can hear, right? It's just a very high frequency signal. You know, you're not going to. So what we have to do is we have to beat with it. In other words, if you let me give you a second here. I think I got a slide here for that. All right.
Does this have anything to do with a beatbox?
Beatbox, no.
All right.
That's a form of
All right. If we have two frequencies you hear, if they're close but not the same, you'll actually hear some degree of beating. You'll hear a little tone difference, which is basically the beating of the two frequencies. So we'll use that principle to help us. Like they're saying, the beat frequency that we hear is actually the difference of the two frequencies. So what we do. Right. So what we introduce is a beat frequency oscillator. So typically for CW, I think the normal is about 800 hertz is a nice tone that generally people like to hear. So what we do is you have this beat frequency, or BFO, running at about 800 hertz different than our IF frequency. So by mixing those two together, the difference of those is going to be an audio tone about 800 hertz. It's usually adjustable, but that's just most people's preference. So, because we introduced that beat frequency oscillator, like I say, we mix the two, and then the difference of them is going to give you whenever it receives the carrier, you're going to get that pulsed 800 hertz tone. With your CW, you're going short or long tones, and speaker or headphones. Not much different
So
there.
where's the decision made, whether it's coming single sideband or whether it's coming CW? Is it in that product detector?
Yeah, it's going to be.
Does it reject one and it selects the other? That part I don't understand. Like, where's it switchable? I guess Dave was
Yeah.
But I thought you had a CW button on, like a.
Yeah, it's a mode, it's selector mode. It typically it's
So
going
it's to
affect the beat frequency oscillator, because for a CW signal, like I say, it's got to be offset by say about 800 hertz. But the other extreme now, for our single sideband signal, what's that? Single sideband suppressed carrier. So now we have no carrier, nothing to measure against to recover our signal. So basically what they call reinsert the carrier. So for sideband, the BFO would be set exactly on our received frequency to replace that carrier that we suppressed back at the transmitter. So now by reintroducing that carrier artificially, now we've got that signal in our sideband, and we can subtract or add the two and actually recover the audio. Because, for example, say we're working on a frequency of, let's say, 7 megahertz, and our upper sideband would be from 7 megahertz plus up to 3 kilohertz. Our sideband would be from 300 to 3000. So now we introduce our carrier at 7 megahertz, subtract the two from each other, right? So now we got that sideband that goes up to 7,000 or 7 megahertz plus 3 kilohertz, subtract it from the pure 7 megahertz inserted carrier, subtract the two, now we get that 300 to 3000 audio frequency back.
So a single sideband would not work without a beat frequency on BFO
No.
line. It needs a BFO.
You need something to subtract from. So you've got to reinsert that carrier so that we have something to subtract from. Otherwise, you're sitting with that sideband from 7 megahertz plus 300 to 7 megahertz plus 3000, but no way to recover it.
So, okay, so now if you got a CW signal coming in, right?
If we're a CW signal, like I said, the
Right,
difference,
yeah.
that's probably part of your selectors. You want to set your beat frequency oscillator about 800 hertz off, away from your signal, so that you get that beating effect,
So
and you
where
actually
does-
get an
where does
audio
that-
tone.
What I
Okay.
can't put my head around is where do you get that selection? Where does that happen? Does that happen on
One of the functions of the selector switch on your radio, because on your radio
Oh,
you'll have
so
a
it's
selector switch
manual.
that'll say you want single sideband
it's
mode,
manual.
or you want AM mode, you want FM mode. That's part of your, that'll be all done by your
Okay.
mode selection feature of the
So-
radio.
We should have that on Saturday.
Okay, but if I was on single sideband mode on
Yeah.
the radio, right?
Yeah.
And I got a CW signal. coming
You'll
in,
hear it,
You'll hear it,
sure.
and you'll hear the dots and dashes.
Yeah,
Oh, yeah.
because as you're tuning by, as long as you're a little bit away from your as long as you've got your variable frequency oscillator a little wee bit off of that received signal, you're going to get that beating effect, right? And you'll hear it. So as you're tuning across the band, you'll hear CW signals, because as soon as you tune exactly onto that CW signal, you won't hear anything anymore, because there's nothing to beat against, right? But as you're going up and down the band, you'll hear CW signals in the sideband mode.
So why don't they just call it oscillator, local oscillator? Because really that's what it is, right?
Well, just to differentiate, because we actually have a local oscillator here serving a totally different function than the beat frequency oscillator.
Yeah.
That's just
Okay,
given terms.
Just the high frequency oscillator, you gotta remember that is to receive the signal from the air, to change it. The other, so that's a high frequency. The other one is more for audio frequencies. There's the big.
Usually
difference.
lower, but yeah. It just they serve two different functions.
So the high frequency oscillator you're saying is for the RF frequency,
Yes.
Yeah, because what we want to do with this,
and that's
so that this is a fairly high frequency, it's going to be fairly close to our received frequency, because we need to take those two to mix them down into give us our intermediate frequency. So these two frequencies will be fairly close together, and this one is going to be way lower than this one.
And whatever.
So then the beat frequency oscillator, is that working with like audible frequencies?
Yes.
So like
Well, it creates an audible frequency, like when we're doing that subtraction, right?
yeah.
So if we get we need that beat frequency to be within audio range of our receive frequency, right? So if we have a CW signal coming in at, we'll say 7 megahertz exactly. So by creating a beat frequency oscillator running at either say 800 cycles higher or lower than that, we're going to, when the two of them subtract out, you're going to get an 800 cycle audio signal that you can hear.
And the next.
Okay? All right, let's see what's next. Oh, come on.
Is the CW one coming up?
What's that?
Yeah.
Yeah.
The
Yeah.
next slide.
All right.
But that's the FM.
That just screwed me for the longest. I couldn't figure it
The
for a
FM
minute there.
one.
What's going on? Yeah, like okay, this is actually our FM receiver. I think we mentioned it. So again, now we amplify it. We have the high frequency oscillator. We don't need a beat frequency oscillator there. All we need is we'll do actually take this frequency and mix it down to our intermediate frequency. Again, like I said, one of the main purposes of the intermediate frequency is we have a nice one frequency circuit, so we have nice filters. We can really clean it up because we only have to worry about that one, basically that one frequency or that one band or frequency band at the IF frequency.
And there could be 2 or 3 IF.
Yes.
amplifiers too, right?
Because every time they do that, it actually cleans it up and tightens it down and makes it
of them
more
do have 2 or
selective.
3, right?
Yeah.
Like I said, we use a limiter just to basically chop off any noise peaks because we don't care about any AM modulation on it. We just want to know what the frequency shifts. And we talked about beat frequencies. We understand that. I have to, maybe I'll do a demonstration sometime and we'll actually show you on the radio. But and they're talking about audio filters for your radio. Well, back not all that long ago, basically most filters are either tuned circuits or some sort of a crystal or mechanical filter that you could add onto your radio to improve the selectivity. But nowadays you're saying more and more they can do them with computer software. DSP term they use quite often now, digital signal processing. So in this case, Peter showed an example of a sound card based filter you can externally on a computer that you could actually take your output from your radio, audio output, run it in through the sound card and use this filter to actually clean up or filter the audio. Just mentioning this point. And every radio basically has some sort of a signal meter, signal level meter. And different value, you have analog ones, you have digital ones, just to give you a very idea of your received signal strength. When quite often they'll talk about signal units up to 0 to 9, and typically what's it say? For a signal 1, which is low, so about, like you're talking about 0.2 of a microvolt. That's pretty low. So you'll get signals typically on HF. Typically 0 to 9. You got really good signals. They'll actually now get into decibels. So you'll say be S9 plus 20, S9 plus 30. For example, so 30 decibels is 1,000 times more signal than S9. I don't know if you guys remember. We need to get into the math of that, but the decibel scale is just a scale of representation.
I picked up Mike at 40 decibels over S9.
What's that?
I picked up Mike at 40 over.
Yeah, okay.
He's
Across the
vertical,
city,
yeah.
eh?
Yeah, he was on. We were on. I forget, 10 meters or something, Mike. And he was 30 dB over because he was so close.
All right, just the fortunate part. This is just kind of for information, even like they mentioned in the book. This is just information purposes because there's no questions on the exam about it. But the latest technology now is they call software-defined radio, where there's a little bit of hardware, but a lot of the functions are all done via software. So that's kind of maybe the latest trend in some radios now.
And that waterfall?
Yeah.
Yeah.
Questions so far? We've gone through it all pretty quickly, but that's basically the gist of what to know. And again, I can't help it, but you do have to basically memorize those block diagrams because there's questions from them. It's back to our typical questions. We'll get close. Yeah, take a break in a couple of minutes.
So, your what do you call your report, or not your report, your meetings,
Yeah.
are they on here? Are they on the computer? There's teacher sheets or whatever you guys
Yeah.
call them. I don't know what you call them.
My notes.
Notes, teacher's notes.
You
You sent me the transmitter, which is.
Yes.
This is great.
Do you want a copy of these ones?
If they're
Once
right,
once I correct the
Yeah.
titles when I go home tonight, I'll.
unless they're already on there, right?
No, they're not, because
they're not on the
there,
list.
there was a set on there from
Peter.
Peter was the instructor that taught it last time. I just decided to do things just a little wee bit differently. I've used some portions of his, but I've added other stuff. So I actually created my own and actually finished them about an hour before I came here, I think.
Dave, if I know Mr. Salangi, he taught me in college, and he's a very specific, probably overload you with information.
Well,
Very, very talented hand.
Yeah.
The guy's unbelievable.
well, we won't mention anything on camera, but okay.
There's a place for that, right?
Yeah.
There's the
well,
time and place for stuff
yeah.
like that.
Well, he builds his own microwave,
Well, it's 10 to 8. Let's take an early break and we'll come back and we'll maybe review some exam questions, and maybe you guys will come up with some questions in the meantime. Then.
Can I ask you a question about
Yeah.
this?